In this tutorial, we will look at FEM methods applied for several other types of cases. In the previous tutorial, we looked at how FEM methods are used for spring elements. But spring elements aren't the only type of problems where FEM can be applied. For example, here in question 2, you can see that it is applied in a fluid flow problem. And in question 3, we have we have question 1 here, which is a heat conduction problem. And there are many other types of problems. So we will see how FEM is applied for other types of problems as well. So for question 1, consider the problem of heat conduction through the composite wall shown. Model the problem using two one-dimensional heat conduction elements introduced in chapter 2. Take the area to be 1 meter squared and solve the global equilibrium equation for the interfacial temperature, which is T2, and heat flowing through the composite wall. Okay, great. So we're not dealing with a spring problem here. So instead, what will be the element equilibrium equation for heat conduction problem? So it will look like this. So for two temperature nodes, T1, T2, point nodes 1 and nodes 2, if heat flows through the wall via conduction, we have the element equilibrium equation. So it's very similar to the spring element equilibrium equation. The spring one will look like this. Okay, actually, you can multiply this constant into each entry of the matrix as well. Okay. So what are the terms that you see here? Here, KT refers to the thermal conductivity of the solid. Okay, so right here, this is a solid. It's some material, and each material has their own thermal conductivity. A is the cross-section area through which conduction is occurring through. Yeah, so if I draw this wall in 3D, like that, and if heat is conducted through this wall, then A refers to this cross-section area, okay, the area through which conduction occurs. L refers to the thickness of the wall, so how thick this wall is. And T1 and T2 are the temperatures at each node. Okay, so it's similar as the previous tutorial. You apply the standard template to this problem here. So here we have two elements, right? So let's draw out the problem. Here we have node 1, 2, 3. Here we have a conduction element, another conduction element, nodes 1, 2, 3. Then they have temperatures T1, T2, T3. And instead of forces, we apply heat transfer into them. Okay. So heat transfer at node 1, heat transfer at node 2, heat transfer at node 3. So what are these heat transfers? Basically, these heat transfer is the rate at which thermal energy is being transferred into the node. Okay, so basically you can think of it as the rate at which you are supplying heat into each node. Okay, so if it's positive, that means the node is gaining heat. If it's negative, that means the node is losing heat. Okay. And yeah, so with that, we can write the element equilibrium equation for, let's say, for element 1 first. So this is element 1 and this is element 2. So for element 1, we have, okay, so the nodes are 1 and 2, right? So we have this here, which is 1 and 2. And then it has a thermal conductivity of what? 20. Okay. So here KT equals to 20. So it will look like this. So here we have KTA over L. They told us A can be taken to be 1. Then K is 20, so this can be, let me write this all out first. So K, T, A, L, okay, we have the square matrix. And then since the nodes are 1 and 2, we can label this 1, 2, 1, 2. Then here is 1, -1, -1, 1. Then this is the temperature vector. So we can substitute whatever we have. So they say area is 1, conductivity is 20, and then the thickness of the wall is 0.02. Okay, so 20 divided by 0.02 is actually 1000. And then I can multiply that 1000 into each of these entries here. Okay, so what I'll get is actually 1, 2, 1, 2, 1000, minus 1000, minus 1000, 1000, T1, T2. Okay, so this is the first element equilibrium equation. So let's move on to the next one. So element 2 has nodes 2 and 3, 2, 3. Again, apply the same formula. So KTAL over this, okay, 1 minus 1 minus 1, 1. Since the nodes are 2 and 3, I can label the rows and columns with 2 and 3. And then since the nodes are 2 and 3, the temperatures are T2 and T3 respectively. Okay, so now you substitute whatever they have. So A is 1, KT here is 6, and the thickness of the wall L is 0.06. So 6 divided by 0.06 is actually 100. So you can multiply that 100 into each of these entries here. So it'll give you 100 minus 100 minus 100. 100. Yeah. Okay. So that's all the elements. We can start to assemble the global equilibrium equation. So the global. Since there are 3 nodes, you open a 3 by 3 matrix. 1, 2, 3. 1, 2, 3. Instead of displacement, it will be temperature, T1, T2, T3. And instead of forces, it will be the heat transfer, Q1, Q2, and Q3. Okay, so now let's go to the first matrix here. So it says here, row 1, column 1, we have 1000. Let me say that again. Row 1, column 1, we have 1000. Row 1, column 2, we have minus 1000. Row 2, column 1, we have minus 1000. Row 2, column 2, we have 1000. Okay, so fill those out. Now you go to the second equilibrium equation. So row 2, column 2, we have 100. Row 2, column 3, we have minus 100. Row 3, column 2, we have minus 100. And row 3, column 3, we have 100. Okay, so fill those up again. And since the two entries overlap, we just add them together. So plus 100. Okay, minus 100, minus 100, and 100 here. So 100 plus 1000 is 1100. And let's see if we can substitute anything that we know. Okay, so we know heat is being supplied into here, and heat will eventually leave through here. And as you can see, no heat is being transferred into node 2. Okay, we're not injecting heat into node 2, right? We're not, supplying heat into this. For example, you can think of it as you're not putting a blowtorch at node 2. Okay, so no heat is being supplied into 2, right? So that means Q2 is actually 0. Okay, so Q2 is actually 0. Okay. Now, what else do we know? Well, they also told us the temperatures at nodes 1 and 3, right? So we can go substitute that. So node 1 is -5, node 3 is 20, And since we have some non-zero boundary conditions here, that means we cancel the row corresponding to that. Okay, you do not cancel the columns because this is not a zero displacement boundary condition. If these entries were zero, then yes, you cancel the columns. But since these are non-zero displacement boundary conditions, you only cancel the rows. Okay, so what we're left with is this dot product with this vector to give this entry. Okay, so at the end of the day, what you have is minus 1000, 1100, minus 100, and then the displacement vector, which is minus. Yeah, even though this vector contains temperatures, we still call it a displacement vector because it is inspired by the spring element uh, FEM model. Okay, so we will still call this the loading vector, referring to the forces that you apply onto springs, and we will still call this the displacement vector, even though it shows temperature. Okay, then here, uh, okay, here it will only be zero because we're referring to the middle zero. Yeah, okay, I'm referring to this zero here. So if you do this the matrix multiplication, in other words, this times this plus this times this plus this times this, you will get 5000 plus 1100 T2 minus 2000 equals 0. And you can see T2 is your only unknown, so T2 will work out to be minus 20 minus 2.727 degrees Celsius. Okay. They also asked us to find the heat transfer through the wall. Okay, the heat flowing through the wall. Okay, so how do we do that? Well, like I said, at node 1, you see, heat is being supplied to the wall, right? So heat is being supplied to the wall, and he is leaving through the wall, or at least I assume he is being supplied to the wall and he leaves through the wall. So what we can do is we know that from this equilibrium equation, from the global equilibrium equation. So let me copy this down first. Hold on. Okay, let me clean this up first. Yeah. Okay, yeah. We know that heat is being, or we assume that heat is being supplied into Q1. So therefore we can change it to Q, which is the heat transfer we are trying to find. And so we can make an equation in the first term, in the first entry, by taking this row dot this column to give that entry. Okay, so that's how this first entry is found. So that first entry is found by taking that row dot that column, so 1000 T1 minus 1000 T2 minus 100 T3 is equal to Q. Okay? You can substitute the values that you know already, right? So we already know, or we are told that T1 is minus 5, T2 is the minus 2.727, and then T3 is, what's T3? T3 is 20. Oh wait, this is supposed to be 0, right? Here is actually 0. Sorry. Okay, so if you calculate Q would be minus 2272.73. Now, why is it minus? It's because here we assume heat travels to the right. But is that true? You can take a look. Look at the temperature between -5 and 20. Which was the higher temperature? 20 is the higher temperature, right? So you know that heat will travel from a high temperature region to a low temperature region. So in reality, because heat is higher here and lower here, heat must travel to the left. Okay? So that's why this negative sign appears, because it's showing that heat actually travels to the left. Okay, so that just signifies the direction, but otherwise the magnitude is correct. Okay, and the next question. Consider laminar incompressible flow in a branch network of circular pipes. If 0.085 cubic meters of fluid enters the pipe per second and leaves out at the ambient temperature, calculate the fluid pressures at node 1 and 2. How much fluid flow takes place in pipe 3? Use the 1D fluid flow element discussed in chapter 2 to build your finite element model. Okay. So it's a bit not obvious what are the elements, but you can reform them such that it's more obvious. So what do I mean? Okay, so here we have node 1, right? Okay, actually, the elements are like this. This is the element. So this is element 1. This is element 2. This is element 3. And finally, this is element 4. Okay, if you want to, you can redraw the diagram. Okay, so you can redraw the diagram. So, okay, let's make 1 into vertical, a vertical line like that. Okay, so node 1 connects to node 2. Node 2 connects to node 3. And then it contains this element, this element. Nodes 1 and 2 together were combined to form element 1. Nodes 2 and 3 were combined to form element 2 and 3. And finally, nodes 1 and 3 were combined. So I had to extend this out. Nodes 1 and 3 were combined to form element 4. Okay, so let me be clear. This refers to this. Then 3 refers to this. 2 refers to this. And finally, 1 refers to this. Okay? Next, what you can do is okay, each of these nodes has their associated pressure. Okay, so pressure here, and T2 has a pressure here, P2, P3 has a pressure here, P3. Yeah, there's only 3 nodes, I think. Yeah, there's only 3 nodes. 1, 2, 3. And then also each of them have their associated fluid flow, right? Q1, Q2, and Q3. Now, what is the element equilibrium equation that we're going to use? The element equilibrium equation that we're going to use is this one provided in the lecture. Okay, so we're not expected to derive it, but then we're expected to apply it. So it's much like the spring element equilibrium equation. It's much like the conduction element equilibrium equation. Okay, so you don't have to care about this internal fluid flow right now. That will be used to find the fluid flow in pipe 3. But what you really have to use is this in front here. Okay, so that being said, okay, how are we going to use this formula? So let's write down that formula. So the formula to use is this. Okay, so the different pipes have different properties, and the properties I mean are the diameter and the length. Okay, so they have different geometries. So what we're gonna do is for all the elements here, so there are four elements, right? One, two, three, four. For all of the elements, we're gonna create a table to calculate this constant here. This whole thing in the front is a constant. Okay, we call it the pipe constant. So I'm gonna call it the pipe constant. So what we do is we draw out the table. So here's the pipe. Okay, we have pipe one, two, three, four. Okay, the pipe actually refers to the elements. And then we have the different diameters, right? So pipe one is said to have a diameter of 7.6. Okay, all of this is in SI units, meaning it's in meters. Okay, then they also have their lengths. So their length is this is just the information provided to me in the question. So now that I drew up this table, what I'm going to do is I'm going to calculate the pipe constant. So the pipe constant is that constant in front of the element equilibrium equation. Okay, because different pipes have different values of this thing, right? So for each of the pipe, I'm going to calculate that out first. Okay, and I'm also going to give this constant a name, Kn. Okay, just to make it short. Okay, because I don't want to have to write this whole thing every time. So I label this as Kn. Okay, so the if you calculate the first value, it will be 2.796 times 10 to the 6, 10 to the minus 6, 3.776. Okay, and then this one is same thing. Okay, so this one is K1, okay, this is K2, this is K3, and this is K4. All these Ks here are just names that I give to these constants because it's such a mess to write this very unpleasant looking number, right? It's such a mess to write it. So just to keep it neat and tidy, I'll just uh assign them some symbols. Okay? Yeah. So that it's easier to do the element equilibrium equation. Okay, so let's go do the element equilibrium equation. So element one is connected to, see, I'm talking about this element here. So element one is connected to node one and node two, right? So that's why I'm gonna label the square matrix of one and two, one and two. And then the constant is K1, right? So this is 1 minus 1 minus 1, 1. Then here is the pressure at node 1 and node 2. Okay, but I can just multiply this K1 into the matrix. All right, so this will be K1 minus K1, K1, K1. Okay, next I will do the same thing for element 2. Now let's take a look at element 2. Element 2, so I'm referring to this, is connected to nodes 2 and nodes 3. Therefore, this is 2, 3, 2, 3. And then now I put this K2 minus K2 minus K2 and K2. Okay, inside here will be 2 and 3 because those are the nodes connecting element connected to element 2. Then for element 3, apparently it's the same thing. Okay, what I mean by the same thing that it's also connected to nodes 2 and nodes 3. And it also has the same constant, or at least the same numerical value as the constant. So here you will label the heading with 2 and 3 because that's the nodes it's connected to. You will label this as P2 P3 because that's the nodes it's connected to. And then here will be K3 minus K3 minus K3 and K3. Okay. And lastly, we have element 4. So element 4 is connected to node 1 and node 3. Okay, so when you write out its element equilibrium equation, the headings will be 1 and 3, 1 and 3, K4 minus K4 minus K4, K4. Then here will be the pressure nodes, so P1, P3. Once we have our element equilibrium equations, we can finally assemble them into the global stiffness matrix. Okay, we have three nodes, therefore we will open a 3 by 3 matrix. Here's the pressure vector. So P1, P2, P3. And here's the fluid flow. So Q1, Q2, Q3. Okay, so inside here we have the stiffness terms. Now, how do we do this? So take a look at the first element equilibrium equation. So in row 1 and row 2, column 1 and column 2, we have K1s. Okay, so we have K1 minus K1 minus K1, K1. Then the next matrix, we have these two. So since the next two matrices are the same, we can just combine them together. We can add them together. Oh wait. No, okay, never mind. I'm not gonna create some confusion. Okay, so let's say that again. Let's look at element 2. Element 2 says focus on row 2, column 3. Sorry. Row 2, row 3, column 2, column 3. Okay, and then we will fill them with K2. Likewise, in element 3, it says row 2, row 3, column 2, column 3 has K3 terms. So yeah, K3 minus K3 minus K3 and then plus K3. Okay, then finally, element 4 says row 1, row 3, column 1 and column 3 has K4 terms. Okay, so plus K4. Row 1, then this K4, then this K4, and this is, so this is minus, minus, and this plus K4. Okay, let me check if my answer is correct. Yeah, that should be correct. Okay, so now what you can do is, you see this K1, K1 to K4, you substitute these numerical values into here. So sub in K1 to K4. Okay? In the end, you get this very monstrous looking matrix. So let me write it out patiently. Okay, then we also have the pressure and finally the fluid flow. So notice that the stiffness matrix is symmetrical. That means we're on the right track. It's not necessarily that we're correct, but we're on the right track. Okay, so next we want to substitute the known values. So they told us that P3 is actually 0, right? So we can sub that in. P3 is 0 and Q1 is 0.085. Because there's no hole at this node, right? There's no hole at node 2, and no fluid is entering or leaving node 2 through like some kind of injection. Like I didn't inject or I didn't extract uh fluid from node 2. Okay, so that means Q2 is actually 0. Okay, Q2 is actually 0. Okay, what I mean is, okay, let's take a look at this. What I mean is, if this was a pipe, right? If this was a pipe, it's not like, if this is node 2, it's not like I puncture the hole in node 2 and inject heat, sorry, inject fluid or extract fluid from node 2. Okay, that's why Q2 is 0. Okay, so going back down, let's substitute whatever we know. So I told you P3 is actually 0, Q2 is actually 0, Q1 is actually 0.08, 0.085. Okay, so because P3 is 0, right? That means this is a zero displacement boundary condition, and that allows us to cancel the row tree and column tree. Row tree. Oh, damn, I didn't mean to do that. Okay, yeah, row tree and column tree. Okay, so what we're left is this and this. Okay, and this. So let's go ahead and write that down. So P1, P2 is equal to the remaining terms. So 3.30 times 10 to the minus 5 minus 2.796. Okay, so if you do this matrix multiplication, you will get, all right? So that's P1 and P2. Now that's P1 and P2. Now we also need to find the fluid flow in pipe 3, right? So how do you do that? So what you need to do is use this formula that was provided in the lecture, right? So going back to here, in the lecture, they provide you the element equilibrium equation for a pipe element, right? This is what we already discussed here. But what this term will calculate, right, are these. So what are these? These are the rate of fluid flow, okay, the volumetric flow rate through each node. Okay, so consider this pipe here. Let's say this is element 1, right? So the rate of fluid flow through node 1 is this term here. And the rate of fluid flow through this space, or node 2, is this term here. Okay? And based on how this is derived, right? Okay, based on the derivation of this formula is based, sorry, let me say that again. The derivation of this formula is based on this diagram. Okay? And take note that the diagram shows that QE1 is flowing this way, QE2 is flowing this way. By the way, the E refers to the element number. Okay, the E refers to the element number. Because here we have 4 pipes, right? So we have element 1, element 2, element 3, and element 4. Okay, but we're only interested in the fluid flow through pipe 3. Okay, so we will apply this formula for pipe 3. Okay, so this here will be K3 for pipe 3. And pipe 3 pipe 3 is connected by which nodes? Let me check the diagram. You see pipe 3, which I'm referring to here, connects nodes 2 to nodes 3. Okay? So that's why, okay, let me write that down. So for pipe 3, we have K3 here. Then since it's connecting nodes 2 and 3, I label this as 2 and 3 here. So this is 1 minus 1 minus 1, 1. And this will be P2, P3. Right? And that will be Q. So this is element 3, that's why it's 3. And this is node 2, so that's why it's 2 here. This is also element 3, but now this is node 3. Okay? So what I can do is just multiply this K3 into this here. Then now I shall substitute whatever I know. Yeah, I shall substitute all the numerical values. So Yeah. So P2 is what I found, right? P2, I found it to be 711.405. P3, they told me is 0. And we found, okay, just now, earlier we calculated K3 to be 3.776 times 10 to the 11 minus 6. Where did I get this K3? Let me just show you. I got this K3 from here. Okay, so I'm referring to this. Yeah, so you can sub it into here, and then you can calculate that Q23, Q33, this will be equals to 0.002687, and this is minus 0.00222687. Why is there a minus here? It's because of the direction, right? As you know, for pipe 3, right, fluid should flow in one direction. Meaning, okay, let's use your common sense first. Fluid should flow like this, right? This is node 2 and node 3. But remember what I said? The formula of the element equilibrium equation, so I'm referring to this. I'm referring to this here. This formula was based on this diagram. And this diagram shows fluid flowing into the pipe on both faces, right? But in order for it to follow the real life flow, meaning in one direction, okay, so this one is correct direction, but then this one, you see, is opposing the actual fluid flow. So if it opposes the actual fluid flow, that means when you calculate it, it should show up as negative, right? You see, they're both the same magnitudes. This and this are the same magnitudes, but in different directions because the formula is derived based on fluid both flowing into the pipe. Whereas it is actually both flowing, okay, one face flowing in and the other face flowing out. Yeah, so that's why there's a negative sign here. So yeah, that's your answer. You can serve this as your answer. Yeah, so that's the first two questions. I'm going to do the next two questions in a separate video.